Alrighty, good morning, everybody, and welcome to the wolfSSL live webinar on the wolfSSL library as a Linux kernel module with wolfSSL engineer Daniel Posner. My name is Kajal Subkoda, and I will be moderating this webinar. All attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the question live, as we will host a Q&A session following this presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. And I invite everyone to follow us on Twitter at wolfSSL, as well as all of our other socials. And please feel free to email us at facts@wolfSSL.com if you have any additional questions. And now I'd like to give a brief company overview before we move on to the technical presentation. So wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2021, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, Fips certification, and a Fips ready offering, MQTT up to the version 5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSOC support and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand it over to Daniel for the presentation.
Thank you, Kajal. So we've just done our 5.0 milestone release of the wolfSSL library. And the 5.0 release brings two exciting new things to wolfSSL. The first is it's our 140-3 code base going gold. And the second is our kernel module, which we've included since the 4.6.0 release that came out in December of last year, now has the capability to be run with Fips 140-3 power on self-test and algorithm testing. So just to back up for a second, Kajal gave you a sense of what we're about as a company. Our marquee product is the wolfSSL library and the wolfCrypt backend inside it. wolfCrypt supplies all of the cryptographic primitives, including various PKCS7 standards and certificate processing, multi-precision integer, and of course, the full suite of the regular AES modes and RSA modes and all the usual stuff. wolfSSL is layered on top of wolfCrypt and implements TLS and DTLS. And as you heard, also an OpenSSL compatibility layer. And we also have an engine mode that allows wolfCrypt to be used as the backend for the OpenSSL library. And that is obviously not something that you would be doing inside the kernel, but it is something that's meaningful to a lot of customers. The wolfSSL kernel module is not just the wolfCrypt algorithm suite, it's the full TLS stack and DTLS stack. We've focused on getting wolfCrypt working smoothly and heavily tested with various build configurations, because most of the use cases that we've encountered so far for wolfSSL in the kernel have been wolfCrypt centric, but TLS is fully ported and is available. inside the kernel. So you can actually do key negotiation. You can stand up a TLS, a completely self-contained TLS endpoint inside the kernel. So we've been working on the Linux kernel module port for more than a year now. The effort started in August of 2020, and it went gold in December of 2020 with minimal acceleration support and no Fips support, and it was basically the minimum subset of capabilities to be able to get something up and running inside the kernel. And in the time since then, we've really closed the gap so that many of the distinguishing characteristics of the library as a whole, such as Fips and highly efficient assembly-based accelerations of public key ops and of AES modes, are now fully functioning inside the kernel. We set out with 3 key objectives for how to make this a convenient turnkey option for customers. The first is to leverage our existing auto tools configuration to allow a single, I mean, it sounds implausible, but you can just add enable-linuxkm and to your configuration flags, and it will build a Linux kernel module for you if user source Linux is actually installed and built and available. And you can use the usual sorts of configure options to enable and disable different algorithms in different modes in order to cut down the size of the built module and include only the capabilities that you need for your application. The way we've gone about it from the start is to make the changes that were needed in order to make the wolfSSL library kernel compatible right in the mainline source tree. So we don't have a separate source tree for the kernel module build. It's all integrated directly in line in the wolfCrypt files and the TLS files. And there's a LinuxKM subdirectory at the top of our repository that has some of the glue logic, the tooling that's needed in order to connect things up. But because we've stuck with a fully integrated code-based strategy, it makes it very easy for us to make certain that we keep our code base aligned with the evolving Linux toolchain. And the last piece of the puzzle, in order to make it easy for us to support Linux as Linux evolves, is that we are not doing an out-of-tree build. It's an out-of-tree code base, but an in-tree build. We use the KBuild toolchain with the settings of the installed kernel. Or the target kernel. It doesn't have to be an installed kernel. It just needs to be a target kernel that you identify with a configure flag. And this is very important because as Linux evolves, the way the KBuild tree sets up compiler flags and linking flags and all of the nuances of the way objects are built evolves along with the rest of Linux. And the same thing goes for the header files, the macros. It's a moving target. I'll talk more about how it's a moving target and what the consequences of that are in a couple of minutes. But in general, by using KBuild and by using glue logic in order to connect up our existing auto tools configuration process with the KBuild toolchain, it makes it very easy for us to continue to support every new minor and major release of Linux. So one of the things to bear in mind is that, and this may not be obvious, but for anyone that's worked writing kernel modules, it's something that you know well. The Linux kernel is not a POSIX target at all. You don't have stack red zones. There's something that's kind of like a C library that's the kernel library, and it provides the usual sorts of functions like mem cmp and whatnot. But you don't have the usual, you don't have SN printf. There's all sorts of functions that you take for granted when you're writing a user application that don't exist in the kernel. So that can be a real obstacle to porting. It has not been an obstacle in particular for porting the wolfSSL library, because the wolfSSL library has been designed from the ground up for embedded targets. And embedded targets have these sorts of restrictions also. So that's actually made it relatively easy to port it. But the list of things you can't take for granted when you're targeting the Linux kernel is this is a very partial list, but you have a tiny stack. It's only 16K. Sometimes it's only 8K. Usually it's 16K. Like I said, there's no stack red zone, so you can't use the area directly below the stack pointer as a scratch area, and the compiler needs to be configured to not do that, because some compilation modes that by default will assume they can use that part of the stack. And KBuild, of course, tells the compiler not to use the red zone. So that's another advantage of leveraging KBuild. There's no thread local storage. Many of the execution contexts in the Linux kernel don't actually have a thread associated with them at all. A hardware interrupt is an execution context. It doesn't have a thread. And if it doesn't have a thread, that means it doesn't have the thread struct that is used in other contexts as a scratch space. So you have to design around that limitation. And the place where that really comes to the fore is when we're trying to support the vector instructions, the accelerated modes in the cryptographic backend. That gets very awkward. You can't just use floating point. We don't use floating point math in the crypto library, of course, but we do use the AVX2 and AES-NI in order to accelerate the crypto operations. And you can't just do that when you're running inside the kernel. And this is true not just of Linux, but it's also true of BSD and whatnot. When you're doing a kernel to kernel context switch, the kernel doesn't take care of the bookkeeping of saving the vector registers and then restoring them when you come back to the context that you left. You have to do that explicitly in your code, and that's very awkward. And another thing that can be challenging is that the Linux kernel headers, not only are they not POSIX, but they date back 30 years, and there's a lot of coding practices that people take for granted now that weren't observed 25 or 30 years ago. And these very old headers can only be included without generating warnings by masking out all manner of warnings. And that can be a little bit annoying, but you learn as you go. And I mentioned that Linux is a moving target. Boy, is it ever. The kernel-specific code in our code base, particularly in the glue logic, has a lot of gating on particular major and sometimes even minor versions of the kernel, because the names of functions, the names of macros, and the semantics of them, the number of arguments they take, changes over time. These are internal interfaces, and when you are running a kernel module, you are inside the kernel. You're not like a process that is hosted by the kernel. You become part of the kernel, and you are subject to all of the correct usage patterns and all of the evolving internal APIs that every other internal part of the kernel is subject to. So there's a sort of a treadmill of surprises. All right, so probably the single largest impact on the code base has been an almost global refactor in order to get stack usage under control. Now, most of our code base has already been pretty good on stack usage, and we have an option, enable small stack, that's been there for years, that is used by in embedded use cases where you have a limited stack. The stack limits in the Linux kernel are actually more extreme than even a lot of bare metal real-time embedded applications. Like I said, you get 16 or 8K, and it's not flexible, and there's no red zone, and that's it. And if you go past that, you crash the kernel, or you generate an exception, and you have to reboot, and it's just game over. So there's no wiggle room in it. You have to work around it. And as I went through this refactoring, we went from 2,684 occurrences of this macro that switches on the small stack build option to 4,897. So more or less a doubling of the number of places in the code base where we've had to special case the small stack use case. The KBuild toolchain, by default, it actually warns on 2K stack frames. Almost everything in our code base now stays well under the 2K stack frame, and it's only with certain build options that you go beyond 2K. We do an internal 4K threshold for the warnings on it. Anytime a use case requires an extremely small stack usage profile, you always have to build it and test it and find out what it is in practice with your exact tool chain and such. So we do a lot of that. The most important quantitative parameter in this picture is the cumulative stack, the high water mark on your stack usage. And we've managed to get that very, very under. I'm going to skip ahead to just show these are the high water marks on our stack usage for various commonly used algorithms. And some of the stack usage that you're seeing here is actually just used by the test harness. So the actual usage, the attainable high water mark is actually below this. These are pessimistic numbers. And as you can see, we're way under the threshold where you'd get in trouble. I mean, it's still like with the RSA, PK operations tend to use a lot of stack. We're still way under control. It's still a big improvement on where it was. Obviously, we had to get rid of all of the recursive functions. There were still several recursive functions in place, and that's a big no-no when you're stack constrained. So we refactored all of the recursive functions, so there are none left in the wolfCrypt library. And as I said, the stack frames on individual functions are almost entirely under 2K. I can only think of one that's not under 2K, and 100% of them are under 4K. And testing is a very big thing at wolfSSL, of course. And over the last year, we've added in more and more automated testing in order to keep out of the code base, keep from being merged anything that would create problems with kernel builds. And the top priority with that was to instrument the high watermark on stack usage per algorithm. And we have had that in place for a while, since late last year. And it's you only have what you test, and this allows us to know every step of the way that we have our stack usage under control. And the last piece of the puzzle here is with algorithms with variable key sizes, you can have a situation where you think you have your stack under control, but because something is snuck into the code base that's putting on the stack something that's driven by the maximum key size that you're going to support, certain build options could expose you to stack abuse. And to that end, we now do a test build where we set the maximum supported public key size to 16 kilobits, and we set the maximum stack frame to 2 kilobytes, which is 16 kilobits, and that catches any and all occurrences of public keys being put, or public key related objects being put on the stack. So we now have 0 instances in the code base of that. And that's another future proofness guarantee that we've stabilized the code base with respect to kernel mode. And I already showed this in a sneak peek a couple minutes ago, but as you can see, I mean, the stack usage for cryptographic algorithms tend to use, a fair amount of stack. This isn't too bad, and we're improving it all the time. So earlier I talked about what it involved to get the existing wolfSSL AutoTools based tool chain connected up with the KBuild tool chain. So as I said, we leverage the existing auto tools configuration as much as possible. And we also leverage the ELF namespace attributes. So we extend the auto tools configuration with a variety of additional options to make it easy to configure for a kernel. And then the auto tools configuration assembles a kernel appropriate set of build flags, and then it hands it off to KBuild. We have a shim make file that is the direct handoff target from the AutoTools environment, and then our shim make file passes to the KBuild proper. There's not a whole lot of logic in them, but one of the key things is we use the ELF namespace in order to define whether a symbol is going to be internal and visible only library-wide, or whether it's for use by applications. And we've been able to use all of our labeling in the ELF header, the relocation table in the ELF object. We read that back in our KBuild make file in order to determine whether or not we should generate a visibility object for that symbol in the kernel. So it just duplicates the exact same visibility that a user space application would see inside the kernel, leveraging all of the work that we've done over the years to have intelligent visibility on each of the symbols in the library. So we have for those of you that are already familiar with the wolfSSL code base, we have a file wc port.h. WC stands for wolfCrypt, and it contains a whole bunch of, it's sort of platform abstraction logic that allows all of our various embedded targets to have an intelligent setup and intelligent macro definitions that make it easy to target each of those targets. The longest section in wc port.h is the section for the Linux kernel. And the reason it's the longest is that the Linux kernel is actually the most complicated embedded target that we target. It's millions upon millions of lines of code, and it's been evolving for 30 years, and it's an enormous body of code. So the abstracting the unusual aspects of the Linux kernel build environment, it's complicated, but it's possible. There's actually very little code in the mainline code base that pivots explicitly on whether you're building for the Linux kernel or not. And that, again, is because we've been targeting embedded targets all along. And that has forced us to use abstractions, to intelligently use macros in order to create an extremely portable code base at the outset. The types of functions that we add for the Linux kernel port, we add a realloc routine. Realloc is not a very happy thing in the Linux kernel. If you're just using kalloc, you can realloc that, but that's a very limited interface. We use the vmalloc as a fallback in order to make certain that we can always have an allocation return immediately and successfully if the memory is available, because we don't need physical contiguity in the allocations that we make for use by the wolfSSL and wolfCrypt library. It just needs to be a workspace that is available through the virtual memory interface. It's not like memory mapped IO where you have to have physically contiguous memory. And I already mentioned the shim make file. I'll actually, if I have time, I'm going to show what these make files look like. I don't know if I think we're probably going to run out of time. And I already talked about that, the ELF, leveraging the ELF visibility. So as I said, Linux is a moving target. There's a new release every week or two. There's the minor, so we have the micro number here, the minor number here, and the major number here. This number changes every about 4 months. And every time this number changes, there tend to be breaking changes in the code base. And we retest the kernel module every time a new release comes out. It's continually tested, and that allows us to stay on top of the breaking changes so that our customers aren't exposed to them. If you pull master, typically you'll have code that will build on the latest stable release of Linux. But we also make certain that the code base continues to build and link cleanly on all of these LTS kernel modules. There are still many people using 3.x line kernels, and we still make certain that we build cleanly there. More commonly is 4.4 and 4.9 LTS kernels, and 5.4 kernels quite common, as is 5.10. So on Halloween Day, there actually was a breaking release in Linux. They renamed the printf routine, kprintf. It became a macro in the 5.15 minor release, and we had to go fix our code base to work around with a version gate. This change in a function that had been around for 30 years. You just don't know what's going to change. So the only way to find out if it works is to test it, which we do. So as I said at the outset, the big deal from the kernel module perspective with the 5.0 release of wolfSSL is that we now support Fips 140 in the kernel. And this is well, I guess for those of you that aren't familiar with Fips, I'll just briefly go through what Fips is. It's the Federal Information Processing Standard for cryptographic algorithm implementations, and it has ECC curves in it. It of course has RSA. It has AES. It has SHA-2, SHA-3. It's a standard that is targeted by any contractor that is dealing with the U.S. government, because U.S. government entities have to comply with Fips, and Fips is a whole process. So you create a code base, you make certain that your code base is correctly implementing all the algorithms, and then you go through a code review process on it. And right now, the code that's in our 5.0 release is in the later stages of laboratory evaluation for the correctness of our algorithm implementations, and the kernel mode changes to the code base are part of that code review. So when that code review is complete, we will have Fips 140 compliant cryptography available as a self-contained Linux kernel module that other kernel modules can use, and it will allow our customers to meet the Fips requirements with kernel mode applications of their own, and that's a pretty exciting new opportunity for our customers. So it's not complying with Fips in the kernel it's actually quite awkward. One of the basic requirements for the Fips cryptographic module is that it needs to be bit stable. A SHA-2 fingerprint is computed across the read-only data in memory after the module is loaded into memory and checked against a reference value, and they need to match. And unfortunately for people that are trying to do Fips in the kernel, the kernel doesn't want to do that. If you're running in user space, you can control where your library is positioned in virtual memory, so that you can stabilize all of the jump targets, the addresses, the pointer addresses to functions in the object. You can't do that in the kernel. It's impossible to control where the kernel is going to put your module. The way a module is loaded into the kernel, the very first step is doing a VM alloc. It's just allocating memory sufficient to hold the module and then copying the module into it. And then the runtime linker, which is part of the Linux kernel, goes through that binary object and updates all of the jump addresses, all the relocations in it, in order to match the actual runtime targets as they exist in the kernel at that moment. And that's not something that a library can control. So obviously, that's going to, that for many reasons, that destabilizes the bit pattern in memory. So that means that right off the bat, you're already working uphill trying to get the Linux kernel to do what you need it to do to comply with Fips. And the solution that we came up with for that was to make the wolfCrypt module be a completely self-contained standalone object and compile it using the PIE mode, the position independent executable mode, instead of the default mode MC model equals kernel that the KBuild toolchain by default sets it up to be. And when you do that, you have to be scrupulous in controlling what types of references you have with internal to your object. There, you can't take function pointers as operands, for example. Those are impossible to make kernel safe in a PIE object. So we refactored it using macros so that the wolfCrypt module does not make any direct references to any external functions, either our functions in the rest of the wolfSSL library or kernel functions. Instead, we have a redirect table that is populated from outside with the jump pointers for each of the external functions that we need to use. And whenever we call them, we do it through the redirect table. And the last piece of the puzzle in order to completely stabilize the bit image is that we use ELF in order, we rewrite the object, we rewrite the ELF object to isolate the wolfCrypt text and read-only data components in separate sections, separate ELF sections. And when the module is loaded into memory by the kernel, those sections stay in memory and are not changed at all. The kernel actually jumps into code that is bitwise unchanged from what was on the file with the module image that was loaded by modprobe or insmod. And it's kind of neat to think that that's the way it works. But the way it works is that the executing code at runtime inside the kernel is bitwise identical to the file that was loaded. That's those spans of the file that was loaded in order to load the module in the first place. So that's the headline obstacle with being Fips compliant inside the kernel, is stabilizing the bit image. And the code that does it is actually in the mainline code base. It's --enable-linuxkm-PIE, and it will actually switch on that build option in order to stabilize the hash. But there's more. There's no thread local storage in the kernel because there are execution contexts in the kernel that don't have a thread associated with them. So it doesn't even make sense to have thread local storage. Our original Fips implementation uses thread local storage for various types of bookkeeping, to track the self-test status on each of the algorithms. And we've also recently implemented access controls around private key data so that we comply with a new Fips requirement that any access to private key data requires two separate actions by the application. And those are natural use cases for thread local variables, but we don't have thread local variables in the kernel. So, it's nonsensical even in principle to talk about them. So what we've done in order to work around this limitation of kernel mode is directly use atomic integer arithmetic. For the private key lock-unlock operation, we just use a counter. It's very simple. We just say the kernel is one big giant application, and if the kernel should be allowed momentary access, if kernel application code should be allowed momentary access to private key data, then we increment the counter, and then we decrement the counter when we should no longer allow it. But if there are multiple kernel threads that are simultaneously performing private key accessing operations, then each of them will increment it, and then each of them will decrement it. And because they're atomic operations, it's thread safe and everything works the way it should. On the conditional, so with Fips 140-3, instead of testing all the algorithms when you first load the library, algorithms can be tested as they are used, which makes startup much faster. But it's not a good match for the kernel use case. What you want to do with the kernel is when you load the module, which tends to be at boot time, you test all of the algorithms at the outset, get it out of the way, and then from that point forward, you know that you can safely access all the algorithms. And typically, the advice is to enable crypt tests in a kernel module build, because that will run the equivalent of test wolfCrypt inside the kernel and verify that all of the algorithms are working correctly, exercise all of the algorithms, and get all of the algorithms marked as tested and safe to use in the internal state object, the internal Fips state object that tracks whether the conditional algorithm self-test has been done on that algorithm. And we've implemented that in a race-free, kernel-safe way, by just using the atomic arithmetic directly. So the final challenge that I'm going to talk about today with getting wolfCrypt to work inside the kernel is vector register. AES&I also uses the vector registers. Getting those to work deterministically and reliably inside the kernel is quite a challenge. The native crypto implementations that are part of the Linux kernel also use vectorized operations, but they can't use them from interrupt handler contexts and such. There simply isn't any direct support in the Linux kernel for doing any accelerated cryptography, or indeed any vector operations at all, or floating point operations at all, from inside an interrupt handler. And this requires that you think very carefully about where your code is running. And that's the type of thing that it's burdensome. It's awkward. And one of our goals was to eliminate that awkwardness. So in our implementation, we actually allocate a scratch space for each of the processor cores. And that allows us, after we've disabled preemption, to safely support vector operations from interrupt handlers. This is an unusual capability, but what it means from an application implementer's point of view is just that you don't have to think about where your code is running. You just have to think about how much stack you're using, and it will just work. The accelerated implementations of the algorithms will function from any execution context in the kernel, not just from a kernel thread. So we think that's potentially meaningful to some of our customers, and we wanted to make things easy, and this was part of how we make things easy. So we do actually have an example use case that you can find on GitHub. We did this as a proof of concept about a year ago. We refactor. Well, it's not actually a refactor. It's actually just a shim.h file with some macros. and no changes to the WireGuard code base proper, just including the shim file and including a .c file with some helper functions in it. But what we did was demonstrated full interoperability with the bundled crypto in WireGuard using wolfCrypt in order to implement all of the algorithms. So you have xChaCha20, which is it's the same as ChaCha20. You just generate the key differently. Poly 1305 as your message authentication mechanism, Curve 25519 for key negotiation, and Blake 2S is the hash algorithm. That's the only crypto suite that WireGuard uses. So it was a particularly appealing target for a proof of concept because it allowed us to target a very restricted algorithm subset. And these are fully functional. You can clone these and build them and load them and have WireGuard up and running using wolfCrypt. These are not Fips algorithms, of course, at least not yet, but they are fully available in the kernel module. So for our future directions on the kernel module, as I said, TLS standalone self-contained TLS endpoints with full key negotiation are already supported inside the kernel, but we don't have sample implementations that use that yet. And that's something that it's probably next up for what we want to demonstrate, because we know that for some of our customers, that's a meaningful capability. Another thing is that the ASNI, ASGCM, it already has a kernel support for ASNI acceleration, and all the PK, the mainline like RSA, Diffie-Hellman, ECC, those are also accelerated using AVX2 inside the kernel already, but we don't have accelerated implementations of SHA, ChaCha, Poly 1305, Curve 25519 in the kernel yet. Of course, we have those accelerated in user space, but our assembly code is currently using disallowed relocations and various other kernel disallowed code patterns. So we have some work to do in order to get those running inside the kernel, and it's on the roadmap. Another thing that's on the roadmap is validation for more hardware. So far, it's been focused on x86 and, of all things, MIPS. We have a full functioning port in kernel mode for 32-bit MIPS. So that's a sufficiently different target that it gives us a lot of confidence that we can get this working in a pretty straightforward fashion on any 4.x or 5.x kernel, 32-bit or 64-bit. For accelerations, beyond filling out the x86 acceleration support, of course, we also want to get support for acceleration on ARM functioning as soon as possible, and also TPM support, because it would be very appealing to leverage secure key storage in the kernel module. And with that, this is just a sample configuration. This is actually a full Fips build. And so we've added in LinuxKM here, and we're showing that's the where the built kernel source tree is. So you just identify that with Linux source, and then we're enabling the kitchen sink. We're doing enable all. It adds everything. We're also enabling AES-NI. That's gonna do both AES and AES-GCM. And we're turning on SP-ASM. That's the assembly accelerations, AVX2 based accelerations of the PK, the public key algorithms. And we're also turning on the runtime self-test using test wolfCrypt that actually exercises all of the algorithms at runtime. Now, it's not much to look at because I have it on quiet mode here. Otherwise, it would be spewing a whole bunch of, actually, why don't I rerun it with quiet turned off, and then you'll see all of the options that have been turned on. Here we go. Usual configure stuff. And the last thing that we're going to have is the list of features that it's enabled. And if I scroll up here, you'll see lots of yeses for all the algorithms that are being enabled here. Is that legible, Kajal? Ish?
Yes, that is legible.
Okay, so the next thing we want to do, obviously, is build it. So that's easy enough. This is the target's a 6-core Xeon. I'll just do make-J6. And building a kernel module using KBuild. Those of you that have built kernel modules, you'll recognize this output. And there it is. That is the crypto signed module ready to load. And now I need to give this window over here the same treatment, reverse video, and enormous. And now we're going to go ahead and load it. Oh, good, it worked. And now we can look in the kernel log, and you'll see this is the these are all the messages from the build. And this here, wolfCrypt self-test passed. That's the module telling us that the kernel equivalent of test wolfCrypt successfully completed. This here is telling us that the Fips post succeeded. And this here is just the boilerplate for the module being loaded and available. Now, if you do ls mod, there it is. libwolfSSL in the kernel, size 3 megabytes because we did enable all. It's giant. There it is, ready to go. And any other code in the kernel, you can now load a kernel module. They would make calls into the wolfSSL library using the exact same API that you'd be using in a user application. It works the same. The code would port directly because we didn't change the API at all in order to bring it up inside the kernel. It's the same API exactly. Any more questions?
No, I think that was the last of our questions. Thank you, Daniel, for a fantastic presentation. If anyone has any other questions or comments regarding this or anything else, please feel free to email us at facts@wolfSSL.com. As a reminder, this webinar is also recorded and will be made available on our YouTube channel shortly after the presentation, so stay tuned for that. And I hope everyone has a nice day. Thank you so much, Daniel, again.
Thank you, Kajal. Bye, everybody.